Yeah, great. So yeah, it's my pleasure to have Dr. Meredith Kramer here today to share some of her work with us. So Meredith did her undergrad at NYU Abu Dhabi, spent the semester here, I think some classes. So I had a pleasure of having a class with her at that time. She continued on and did her master's and PhD at Northwestern under supervision of Dr. and now she's currently working in New York at a Deutsche Bank and as a consultant. And she's interested in engaging with us and seeing what kind of opportunities we might have to collaborate on some research. Right? So I'll let you introduce the topic.
Yeah. Thank you guys for being here. And I'm really excited to present some of this work. This was some of my dissertation work that hasn't seen that much of the light of day. So really interested to hear any suggestions or questions that might drive it forward a bit more. I think that we'll find out from the other students that sometimes you're at a crush right at the end. And there's so many things that you have ideas for that we wish that you could have continued and refined a little bit more. So with that, let me go and have a quick next slide. Some of the motivation for this research was as cities are facing increasing congestion and mobility transit shift, we've seen ridership on transit not down from pre-COVID levels. And at the same time, since 2020, we've seen a huge boom in bike share and the rise of micromobility in the wake of the pandemic, but also has continued to be steadily growing here, which is really helpful. It can address sustainability, equity goals, help improve our ability to have this additional alternative. But making sure that the infrastructure is in the right place to support that transition is really important to help making it actually successful to have that widespread adoption of bike share in different cities. Oftentimes, some of the implementations are pretty short-sighted or limited in scope, whether that be budget or different constraints that cities face. These are a couple of examples. My work at in Evanston, from Evanston to Chicago, where Northwestern is, where the Transit Alliance says that where the bike trails end is Evanston. So there's all of these disconnected longer paths that just end and are disconnected in the city of Evanston. Likewise, recent improvements in bike lanes are based on corridors. So in Chicago, this is a 1 mile corridor of a bike lane with knowing that people are traveling to different destinations. One corridor isn't always going to make a continuous, safe and protected route for people to begin traveling on, which then undermines the value and potential really of micromobility and creating that increased mobility share, congestion reduction, and things like that. So this work focuses on the network effects of bike lanes and congestion dynamics through a bike network design that makes use of NFDs, and also NFDs today for long. We also include equity objectives in these formulations. So looking at what are the trade-offs for, and these are lack of trade-offs, and some equity-based design principles when thinking about bike lanes at a whole network level. This can all, I think the Google Docs formatting isn't PowerPoint format, so bear with me on that too. The basis of this work begins with the network fundamental diagram, which is the network-wide relationship between flow and density across vehicle types. We know, and it's been found that it's dependent on network topology. So things like perimeter control, there's been a lot of work on that, or signal design and its effects on the NFD. So it's useful then as a traffic performance measure. This relationship has been extended to many different modes. Bikes are one of them, but also pedestrians, buses, and those mixed interactions. There's even different animals, NFDs. So there's one about ants forming a flow density relationship in their ant colonies as well. Because it's been extended to different modes, we see in pedestrian dynamics that there's this width-based measure where over an area, there's different dynamics because of the self-organizing nature of lanes. This behavior has also been seen in cycling, where once you have wide enough area, there's an overtaking that is able to occur. And so when thinking about designing bike lanes, the width is a very important attribute. And from a network standpoint, treating them more like pedestrians than cars, by including that width-based to create an area-based fundamental diagram is especially important. And then likewise, another key element of bike lane design from a user safety experience perspective and perception, but also including that width element is separation. So if you can imagine on a street with very little car traffic, without a bike lane, the bikes can actually use that whole width of the lane and would be traveling across that whole area versus like if they had a bike lane that was fully separated. There's this level of interaction that are important design elements for bike lanes. So with network dynamics and these separation elements, I developed this network design process, first starting with simulations. So simulating varying amounts of bike lanes in the Evanston network in mostly random configurations and extracting those flow density observations. I then estimated parameters used in standard functional form and then modeled parameter relationships to network attributes. So whether that be the area or the amount of interaction that is happening between bikes and cars in this case. That leads to a whole functional form of the NFD where the inputs are those attributes of the bike lane that are important. And that goes into a flow optimization. So trying to find the maximum flow combined between cars and bikes that has a certain amount of area dedicated for each mode or aggregate modes. The last step is a link selection optimization. So based on those broad attributes of how much interaction can we accept in this network, how much area should we dedicate? What then is the link allocation throughout the whole network that could create a network that meets those high level attributes? I'll go into each of these steps one by one, but so you have the roadmap of where we're going, and then also, of course, feel free to ask questions. Like I mentioned, we'll be defining the NFD based on these definitions using the area-based measurements. So here, rather than thinking about the length of the network, we think about the area of the network. And that is the area that's available to that particular mode. So whether that be the bike lanes or the car network, they have different areas available to them to travel through. And so these are the three different types of areas we look at. So a shared area, a micromobility lane that's not separated, and a separated micromobility lane. And I'll show you how those go into each bucket later, but just to set some of the grounding. This is the Evanston network. It's a pretty small network and it's a lot of residential and like low speed areas. Notably, there is like a long corridor here where bikes are explicitly not allowed. So that would be like the fourth type, the type 0, where bikes are excluded from the network. But when you think about all of these links, there's actually very little that is part of the bike network, and we can see how disconnected a lot of it is. So these are painted bike lane corridors here, and they do have this one continuous long corridor of separated bike infrastructure that go kind of like cuts across everything. But you know, interventions like this, where it's completely disconnected from the network, are very motivating for this work. What's someone going to do with 3 blocks of bike lane? So the first step of this work is simulating scenarios with varying amounts of bike lanes and varying amounts of separation. So for all of the links in the network, I assigned them to one of the types, varying from 0 to 100% of them being a painted bike lane, and then 0 to 100% of them being a separated bike lane, and then interactions between those. And the simulation work was all done using SUMO. this is part of the motivation, again, for using, yes.
Quick question.
Yeah.
When you say 0 to 100%, so what happens when it's like X%, 20%? How you're randomly assigning?
Yeah, randomly assigned links. So, like all the way from no bike lanes to like 20% of the bike lanes being, so like 40% of them having a bike lane, and of those 40%, 20 of them being a separated bike lane. All the way to every link having a bike lane and every link having a separated bike lane.
So every time you change the percentage,
Yeah.
generate.
Yeah. So each of these colors and shapes is coming from a different one of those scenarios. And I did it 20, 40, 60, 80, 100. So quite a few different ratios to be looking at. I think there was a limitation of this work to point out in the beginning is random links probably don't yield a realistic network. But for the sake of experimentation, random links make the most sense for unbiasing the results. So these are the length-based definitions, right? So here, the amount of the denominator of the EDC definitions is the length of the network. And you can see this makes a sensible curve for cars, like there's some scatter depending on like how many bike lanes are here. But really there's no relationship between the different types of treatments for bikes and the amount of peak flow that they achieve. But by looking into the area-based definitions, we can see a lot more separation and see really where the effects are coming in. So the most separation, because it's limiting the interactions, is yielding the highest throughput of flows versus the bikes are still routing through the network and interacting and slowing down the cars, and vice versa in these lower scenarios. There's quite a lot of bikes and cars to be able to be reaching these kinds of curves. But you can see, right, like in the free flow regime, there's very little difference between each of the splits. But as we get to that level of congestion, separation becomes even more important to ensure that those interactions aren't happening. And that's what we will be looking into to design the network based on these findings. So the next piece is getting the estimation of the functional form. So here I'm using the functional form with physical meaning by NYU's Monica Menendez, of course, which is based on free flow speed, capacity, jam density, and the backward wave speed. So with these simulations and those resulting curves, I estimated a value for each of those variables. And then having values of each of those for each scenario, I then modeled their relationship to the network attributes. So let me go over the network attributes, introduce them to you, and I'll show the models. Between the three different treatments, these fall into different buckets of area. So the first bucket is shared area. So when cars and bikes are interacting in a lane, that goes into the shared area bucket. So any length any length and width that is a shared area type 1 treatment, which is no treatment, goes into that shared area bucket. The vehicle lanes, when there isn't any separation, so when bikes could, as the spiker is doing, begin to overtake and still interact with the vehicles, that also falls into the shared area bucket. Exclusive micromobility lanes where really cars shouldn't be driving falls into the bike exclusive area. And as well as any separated micromobility lanes where they have that hard separation. And then finally, in the separated scenario, the car area then goes into the car exclusive area bucket. Oh my gosh, this really didn't translate, and it's a weird graphic. I'll try to explain it. And I'll show you, send you the real layout from PowerPoint and have Google Drive later so that it helps. Okay, this is our 3-lane wide lane. Without a bike lane, there's 2 lanes for vehicles to interact between. So think about the stripes on the ground. That's kind of what we're measuring, is the stripes on the ground. And that would be these 2 yellow stripes that are interacting. So then we're counting what I'm calling the interaction plane length. And it's 2 times the length because there's 2 places for vehicles to interact with each other. That's the same for a bike lane that does not include separation. There's still that same amount of length where interactions can occur between vehicles and vehicles or bikes and vehicles. But in the separated bike lane, there's only 1 interaction plane, and that's only happening between the 2 vehicles because there's a hard buffer separating the bikes that they can't have those interactions with other vehicles. So those 3 pieces, each of the modal areas, the interaction plane, and then the total area of the network are the network attributes that we're looking at to estimate a next step functional form of the NFD. So I replace each of the these with, so this is backward wave, jam density, and capacity with capacity, jam density, backwards wave with a modeled formula that is based on these attributes. So this is a function of the total area of the network and the interaction plane of each mode's area and the total area of each mode's area and the total area as well. And all the scenarios, the free flow speed, as you could see from the graphs, was the same. So I just used that estimated value to build out these curves. So these are a couple of different simulated examples where you can see the fit between the simulated points, which are the dots for cars and micromobility, and the actual fitted function itself. Now let's make it more complicated and optimize those. So the objective, okay, let me go back to here. The objective is to optimize the sum of these flows. So auto and micromobility peak flows is what we're maximizing. And then the constraints are based on not exceeding the total area. So we can't create more area in the network. We can't create more width on any given link. We need the critical density to be less than the jam density to make a reasonable curve, and then making sure that any of those attributes are non-negative. This was solved with IPOT to find what of those 3 features maximize the combined flow of cars and bikes. This is my next formulation. This is what the resulting NFDs look like for cars and bikes, where you can see that this is the amount of area. So we should have about an equal allocation of car exclusive and bike exclusive area. When you think about that on a network, that actually really means almost every link should be separated when reaching these peak flows. There's a little bit of shared area, and the interaction plane should be relatively small, which also reflects having these exclusive areas as well. So with these curves, like this is what we're aiming for. We know what area needs to be for the cars. We know what it needs to be for the bikes, how much interaction plane we should have on this aggregate network-wide level. And the next step then is breaking that down into links. So what are links that could be added up to make these this optimal network possible? which has quite high peak flows. So we'll use the distance between any estimated NFD curve based on the attributes to that optimal curve and try to minimize that distance while maximizing accessibility, resulting in a set of links that should have certain types of bike lane treatments on them. And then this is subject to budget and space constraints, which would all be here. But generally here, there's an accessibility maximizing. So the accessibility is based on how many other zones a trip could access within 20 minutes by bike and by car. And then taking into account that distance between what the optimal is and what the actual is, which I have more graphics that will explain a little bit better. I used a realistic Evanston annual construction budget and looked at what the construction costs are. There's a trade-off because painted links where there's no separation are quite cheap versus like building in that hard infrastructure that comes into play. And then all of these kinds of conservation, keeping the total area consistent, non-negativity also apply as well. So these are the different zones. And so for each of these census block groups, we calculate the distance to every other zone, and based on the free flow speed, convert this into a travel time. So then if you're in this zone and it takes you 20 minutes to access all of these zones, but like this takes 25 and just takes 30, they wouldn't be included in your accessibility. And so we're maximizing the total number that all zones can access in this formulation. The travel time or the distance is also weighted by the cyclist stress index, which allows for is preferential towards those separated bike lanes, where the weighting of the trip is higher if you're in a high stress scenario that's based on the speed of the links next to you, as well as the amount of separation that we are having in that particular zone. So these are the results in the NFDs. So we're not really able from the aggregate to disaggregate the links into the exact amount that we need to achieve that optimal form. Thus, that's part of why the objective is to minimize this distance. You can see there's a lot more potential between bikes than cars, but this is also highly due to the budget constraints, where the separated links are exceeding the budget, and so trying to still create cyclist area means that we're not fully meeting, we've been very close to what the optimal amount of separation would be for cyclist traffic. And then finally, this gives us a network. So I'll go through some of the networks. What we see here is there's different coloring for the different types of bike lanes. I should also say I solved this using a genetic algorithm. This is probably one of the biggest areas of future research that could be improved here. That the solutions, well connected, kind of are a little unrealistic for the real world, because you can see it's just kind of a scattering of bike lanes everywhere. Again, that's focused on maximizing flow, and that's where we get to that from. But in terms of like what we might actually want to be seeing, this doesn't prioritize or say like what are the most critical links to completing this network, and that could also be another area for research. But you can see here, this is the separated bike infrastructure. It's much more connected, especially through this like central core of Evanston, and then up through these like neighborhood streets. We have all of the separated links. Similarly, anywhere there's not a separated link, there's pretty much a painted bike lane. and very few areas without bike lanes. Okay, I'm gonna do a pause before I add in the equity part and see if anyone has questions or, yeah, that makes sense to you. Everybody, love to hear.
I have a quick questions in page 24. I think that the before there is a what does the big difference between the car and bike. I think, but why it seems like similar are not.
Yeah, so part of the bike estimate, like there's a couple of reasons. I included some e-bikes in my distribution of bikes to test. The goal was to test eventually the difference between e-bikes and regular bikes, so they have high speeds. But Evanston is also a quite low speed network to be looking at. I think the highest speed limit is 30 miles per hour there. And they keep reducing it. So there's not actually very much of a difference on like such low speed networks. And there's also a stop sign on almost every corner. It's also just kind of a characteristic of that particular network. So it's both of those things together.
So when you're adding, you're creating links or adding capacity?
Reallocating.
Reality.
So like
car space, or
Yeah.
shared space.
Yeah.
So when you're optimizing that design, you're losing flow capacity for the
For the cars, yeah.
And the result that we got was to the show just kind of distribute
Mhm.
a little bit.
Yeah. Yeah.
So you think it's the brand that might be because it's using an NFD, which might not be able to distinguish.
Yeah, I think that's that. I think that it's also the solution methodology. I think there's a couple of things, right? So I think that the genetic algorithm, because what it's doing is like taking the best, like what's performing the best in terms of minimizing this curve and accessibility, and then like mashing them all together, right? Like that's the genetic part, and then like saying this is like the best, and then continuing to create new solutions, pick the best ones, and then make some combinations. So in the mashing together, I think that's where things get really random. But I do also think that part of it is about the NFD, and that like all we're trying to do is like hit an area value. Like we're trying to hit a level of separation, and that's not saying connectivity, like that's not like saying like a safe path for all origins and destinations. And then like when there's not often extra budget, we're always hitting the budget, but like at some point we're just ending up with like links a little bit randomly because there's not like a value to that link kind of, but there's a value to reaching the area level that we are looking for.
Yeah, like when you have, let's say, for the same amount of miles, you have one connected route or versus the same link kind of distributed everywhere. Like in the real world scenario, it would be like differences in bottlenecks that form, things like that, right? But is your model recognizing? No, it's not.
No, it's just trying to like work with this function to get it closer to the optimal, but at the same time, I mean, there's a couple of things, right, too, because then this function is based on the random network as well.
Right, I mean,
And so then it's like too random.
yeah, because the NFD itself, it's assuming kind of like a homogeneous
Yeah.
network, but you're using that assumption.
To then allocate it so it's only like with that function.
Yeah, I mean, so in terms of like the output, because you're using that, you might not be able to really designate where are the routes, but the number of mileage like still makes sense.
Yeah.
But,
Agreed, though.
And then the accessibility objective.
Yeah.
I know we can't see it.
Yeah.
So it's like based on like a gravity model, or is it like just in terms of like finding the shortest path travel time?
So the centroid of each zone
Yeah.
is being routed to the centroid of all other zones
Yeah.
using shortest path.
Yeah.
And then we're counting the number of zones that are accessible within 20 minutes.
Yeah.
From each zone, so that it's summing the total number of zones that are accessible to each other across the whole map,
And that's you're maximizing.
maximizing.
Okay.
Well, I have a quick question. Well, my intuition is that the design of separate lanes are the best design.
Yeah.
But the final turns out to be a mixture of both type 2 and type 3. So could you explain a little bit about this inside?
Yeah, that's largely due to the budget constraint. So if we were really looking at, let me go back to the values. Here, if we think about what these values mean, and remembering that basically this means that, the whole network should be that type 3 bike lane where there's separation, because that's the only time that those areas go into exclusively car, exclusively bike. But the budget constraint is limiting that the ability to make every link that type 3 a fully separated bike lane. Like trying to capture the trade-offs realistically, but yeah. But I agree that that is often the case, but it is a little unrealistic to have everything be separated.
Thank you. And so the orange lines on page 24, they are based on the optimal flow is based on all of the things are separate lanes.
Yeah, exactly. That's kind of what the area breaks down to looking at that. Which from the simulated results also makes sense and is what we want to see. Where having all of the bike lanes be separated, which is this yellow diamond, is the highest flow that we're seeing from simulated results as well. When we measure by area, when measuring by length, which is like what we've typically done for cars only, we don't see that relationship.
One more
Yeah.
thing about the accessibility. So
Yeah.
so you're counting OD demand. It's like rated by OD demand.
No,
No, it's just
like-
summing all the
all
for
this,
every OD pair
yeah,
within 20.
is it
Yeah.
20, exactly. And I actually, this probably will help. Like to. We can't,
Yeah, because I think that might be another reason
yeah,
you're getting such distributed results.
yes,
Yeah,
because
because
it's trying to go everywhere.
Yeah.
Yeah.
whereas if there's weight on the probably see more well structured corridors that come out of it.
And that's kind of what the ethical designs will show as well, but we have to have the inclusions. So. This would be really hard to talk about. I should have done with the percent. Okay. Maximize the total accessibility. This is where we started in the formulation. This is the utilitarian objective. So summing all of the zones, both modes, access in 20 minutes, given a certain set of treatments. The other design formulations fall into 2 categories. So these first ones here, sufficiency and accessibility gap, are constraints that are applied to the problem. So the sufficiency criteria is that everyone should meet some threshold of accessibility. In this case, it's 45 minutes. So while we're still maximizing the accessibility of all of these zones to be accessible in 20 minutes, there's a constraint where no zone can have an accessibility below 45 minutes, which is kind of immense and small. So in different cities, that might be a different number, but for this development, it was that every zone should be able to reach every other zone within 45 minutes. The next group is in the accessibility gap. So this is taking the worst off and the best off and making sure that there is a small gap between those. And that comes in 3 different attributes. So between cars and bikes, there should be a minimum gap this is income based. Lowest and highest income shouldn't have a gap. Between bikes and cars, there shouldn't be a gap, and this is all based on that accessibility calculation. And then between the lowest and highest accessibility zones, keeping that gap low. And then the last group is to maximize the least advantaged group. In this case, then it would be low income bikes compared to cars, and then the lowest accessibility zone. And for these 3, this is a change in the objective function compared to these other 2 that are a change in the constraints. So rather than maximizing total accessibility, then these are maximizing separately each of those groups of people or zones.
I mean, but when you look at those kinds of gap-based approaches, might just encourage you to knock out.
Yes. Yeah, exactly. Because it's just like saying like, oh, the high income should have accessibility. Yeah. And the next slide shows us this too. Those don't result in like the best solutions holistically. It does exactly that. So here we're comparing how each of those formulations compares to the existing network. First of all, is here across a couple of different metrics. So the total accessibility is the first point here. Bike accessibility, car accessibility, the accessibility of the least accessible zone, low income accessibility, how close it gets to the NFD form, and then finally the construction costs. So at a glance, you can tell that when it comes to these accessibility gaps, they're always maximizing that attribute that they're focused on. So they're achieving the highest, like this is in least access, right? So they're achieving the highest, and it's at the expense of all of these other accessibilities where they're focused on that one. The solutions are focused on that one factor. But actually, one of the key findings of this is that these and I think some of this is particular to Evanston, but that these maxing in across mode, income, and accessibility are actually some of the most holistically best solutions that are hitting high levels of access for cars, for the least accessible zone, for low income access across all 3 of them. They're performing kind of the best at a glance. And thinking about travel time as well, there's small increases in total travel time in the whole network. The utilitarian solution does have the only time where the travel time and total travel time is reduced compared to the existing network. But the increases, especially like for maxine and mode, is pretty minimal.
What's the like the 10 o'clock?
This one,
Yeah.
construction cost.
So
here-
existing has costs.
This is actually inverse, so it's 0 out here, and then the lowest construction cost would be the closest. So the maximum income has some of the lowest construction costs.
Oh, so small.
Yeah.
Better.
Yeah.
That's kind of counter.
Yeah. Yeah. But I didn't want to say that like more construction costs is better
Right,
either.
But then, can't you scale them?
Yeah. The opposite
That's
way. I think that would probably make more sense because it always looks like this chunk of.
Yeah.
It's like a long. So I'll focus just quickly on showing you some attributes of the maximum solutions as examples of how this can play out more. So here's the zonal accessibility. And across the 3 different formulations, there's not so many differences, but importantly, there's kind of a function of the map, right? That these zones are further away. They have the lowest accessibility, whereas like the more central zones then have higher accessibility. But when we optimize only for bike accessibility, this leaves some gaps in the southern part of the city. This is notably a lower income area, which is why the maximum income has some of the highest accessibility for the southern part of the map.
Quick comment on this, right? So you're saying that the edge zones have lower accessibility, but is that because of by construction of this study area, right?
Yeah.
So like they have access to
Other areas
outside
that are
this,
outside of
and
it.
you're not keeping that into account.
That's definitely, I mean, and just having like this out zero part, it's definitely a function of the study area and also a function of the design. But for this lower part, you can see like where things are more a function of the design, that the lower income area has higher accessibility in the maximum design. These are the networks. There's a lot of the type 2, or just the painted infrastructure in these more neighborhoody areas. So this is like probably the most low density residential part of Evanston. So we see a lot of networks of painted infrastructure, whereas to get that accessibility for these lower income southern areas, there's a lot more separated bike lanes that are allowing that north-south access, which is, again, partially layout of Evanston, that is where the most accessibility was built up to have those separated bike lanes. And in each of these solutions, there's also an emergence of corridors, so making sure that or the solutions found that those connected type 3 lanes not only contributed more towards that active area, but then in terms of maximizing accessibility, that was important to solution. Thinking about some of the trade-offs in comparison to the current network, the maximum income, so income-based and accessibility-based metrics improved accessibility overall compared to the current network for all zones. However, only focusing on bike access, there's 2 zones that actually lost accessibility compared to the existing network. And a part of that is some of the nature of the solutions being that like randomized process. Okay. I'll do key findings quicker and then ask more questions. But this work was an extension of area-based measures in NFD that were previously used in pedestrians for bikes, allowing for that lane dynamic to be incorporated. I developed a predictive NFD functional form that helps estimate these unbuilt designs without simulating them every time, and use that then for an optimization framework to select links to design a bike lane network, and then found that some of these equity based designs actually have limited trade-offs compared to the utilitarian design, and that there is value in some of those choices that often, I guess, isn't it's usually a dichotomy between those choices. Areas for future research would be thinking about the generalizability of this functional form across different cities and contexts. Looking into additional modes being added to the specification. Especially there's a lot of work looking at bus and cars, looking into more structured optimization methods, and I think even being able to limit some of that randomness that's happening both from the NFD but also from the genetic algorithm. And then a lot of the underlying motivation was for this work is focused on like how can we make a connected network and how can we model these effects on a network level, knowing that that's important for traveler behavior. So being able to incorporate what that really is, or to say that more is lots of thoughts there. Any other questions?
Questions, other questions? I have a question. So I'm wondering, oh, yeah, they have a panel style, so we don't see it.
Yeah, I don't think there's.
Yeah, it's there, but you don't see it.
Okay. Would people like raise it?
I think Lizzie.
Okay, fine.
Oh, yeah, sure. So, did you try not using it or just doing it?
Doing
network?
No.
I mean, it's large, but it's not too
Yeah.
unmanageable. It seems like you could.
See like what
Yeah.
happens if we take out the
Yeah.
like minusing the area. Yeah.
Yeah, I mean, it might be able to, you might be able to solve it.
Yeah.
Fast. Fast.
Yeah, or I mean even right like the accessibility maximizing. Yeah. I think that would be a good baseline to be comparing solutions to for sure. I think a lot of this was based on, like the existing network or the utilitarian solution, but I think that makes a ton of sense as like another baseline.
And then, how generalizable I think you apply it to Evanston, but some parts of it, especially because you're randomizing different configurations, it feels like that part can be transferable to other.
Yeah, I think it just, in terms of generalizability, right, like the coefficients of the jam density model, would likely be unique for each city, but resimulating, like randomizing and resimulating, and deriving new coefficients seems to be pretty generalizable.
Yeah, it's like 50. I mean, I guess the network itself, once you start finding that's very specific.